Hello, my name is Danielle Marceau. I'm professor at the University of Calgary in the Department of Geomatics Engineering. I'm the director of the Geocomputing Research Laboratory, and for the last almost 10 years now, with my students and collaborators, we work on cellular automata modeling. So we develop cellular automata models specifically to simulate land use changes. With my former PhD student, Leandri Moreno, we have developed an object-based cellular automata model, and this is the topic of my talk today. So this idea comes from the fact that what I call conventional cellular automata models are based on a representation of the geographic space that is arbitrary because it subdivides the geographic space using a grid of uniform cells. As we all know, there's nothing that looks like cells in the landscape. Actually, what we perceive in the landscape is rather a collection of objects, which are entities of the real world that are meaningful to us. A street, a house, a piece of land are objects, the way we perceive them. So this is what we want to reproduce in our object-based cellular automata model. Also, previous studies that I have done and other people as well have done show that the representation of the geographic space using regular cells doesn't provide an adequate representation of the space. Of course, it has an impact on the simulation results. So the idea of developing an object-based cellular automata was to overcome the limitations of the cell-based CA model and see how more realistic we would be able to represent the geographic space when we do simulations with a cellular automata. So the idea behind this object-based cellular automata is to first identify those objects. So we use remote sensing images, and now with the new segmentation packages that we find in remote sensing software, it's relatively easy to identify the objects that we want to work with from a remote sensing image. And these objects that are represented in a vector format can be used for the calibration of our cellular automata. So that's what we did. We had a series of vector maps showing the objects at the scale at which we wanted to work at. That was representing the objects, the initial objects for our simulation. The other good idea that I believe we brought in our model is the idea of a flexible neighborhood. So again, in a conventional cellular automata model, the neighborhood is defined topologically. Very often it's based on the concept of distance, which is a good concept, but it's an arbitrarily defined distance that could be of the first order or second order because we're talking about a local neighborhood, or it could be a very extended neighborhood, but it's based on topology. What we wanted to find here is two things. The first is that we wanted to get rid of the arbitrary criteria or criterion used to define the neighborhood. That distance is something that it's difficult to evaluate. And in conventional cellular automata, it's always the same distance that is applied across the whole study area. And the first thing that we wanted to do about the improvement of the representation of the neighborhood was to say, can we define a neighborhood that would be specific to each object? And the second, I would say, novel idea that we brought in our model, that we implemented in our model, is this idea of a semantic neighborhood. So a neighborhood that is not just based on a distance, or again, the topology. So a semantic neighborhood means that we look at what is in the neighborhood of a central object. So the concept of distance is still important, but we say an object in the study area can have an influence on the central object, because between these two objects there's nothing that will act as an obstacle of the influence of that neighbor to the central object. So we call it a semantic neighborhood because we use the state of the objects, not just the distance between these objects and the central object, to define the neighborhood. So we tested this implementation in two study areas, one in Quebec, one in Alberta. We used two very different study areas in terms of their spatial organization, the spatial structure, and we were able to show that the representation of the geographic space was quite improved when we used the C that incorporated the concept of object base compared to a raster-based cellular automata. Now, the limitation, though, that we see about the C model is that handling the topology is very computer intensive. So we're working on this at the moment. We also want to test this idea of a semantic neighborhood in different geographic contexts, see if it makes sense, maybe find a more refined definition, and make this object-based cellular automata really operational for real studies, so it won't take days or even weeks to run simulations, but it can be done in a reasonable period of time. And I also would like to mention that if you want information about these implementations, we have published 3 papers. One has been published in Environment and Planning B in 2008, one in Computers, Environment, and Urban Systems in 2009, and another paper has been published in Photogrammetric Engineering and Remote Sensing in 2010. And so these papers are available. Again, I want to mention that the main author is Dr. Niandri Moreno, who was my former PhD student, and myself, and sometimes other collaborators. I hope this was clear, and I say bye for now.